Okay, sick. Okay, everything's sorted now. Let's go here. The tutorial. Okay, so we're going to look at example 9.1 to start in the green book. And the reason why is because we have answers there, so we can just check that we're doing everything right. So that's page on module 5, page 7 of module 5, or page 39 if you go to the electronic thing. Let me just show you that. So green book. We're doing green book example 9.1, module 5. So in the electronic version, it's page 39, around there. And if you go from module 5, because they start the numbering from the module, it's page 7. Okay, are we all there? They're on the same page. Let me get the question. So do you guys start trying to do this thing meanwhile? Just it'll be good practice. Let's see, let's compare answers as we go, even though the answers are there in the book, but just for you guys to interact. Okay, let me get it here. We'll just shift. Sorry about everything, all these technical difficulties. Here we go. Shame. I'm also very sorry for the people that's marks are lower than what they're expecting. But actually, it's a very good thing that I saw that there was something weird, because I was getting a few queries, and then like I could just see something weird was happening. And so it's actually better that we all get out the actual marks that we deserve, definitely. But yeah, that's a bit sad. If, like, I know some people's marks did lower, quite a few people's marks lowered actually. So yeah, but luckily this thing's only for 3%. Like one quiz is like 3% of your marks, so it's better that you have an honest indication. That's way more of a useful thing, so that for the exam you can know what's happening, and you have all your answers that you typed in there. Also a good prep for the exam, because the exam's going to be a kind of similar system where you have to put in like dots, no commas, dots, no units. So like if your answer is 6, we'll put a comma, 0.38 volts, and I say to one decimal place, then that means it must be 6,0, not comma. Dot, full stop, 0. The reason why is because this system that we're working with now, Canvas, it's not so good for engineering subjects, and there's lots of problems, but it was just something that they could just put online. For now, we temporarily in an online phase. So there's a few limitations that I've had to work around here. But comma, why we don't want comma, even though we use comma, is because of, I don't know if you guys know of CSV files, which is a comma separated value. So they delimit, or they separate their answers with a comma. So if you write your thing with a comma, then it makes a bit of a problem if I need to make my own post-processing, because their system actually just isn't good enough. So I've actually had to code my whole bunch of stuff to make it work. So please do that. Don't include this fault either. There's only one person that actually did this for one of out of their 11 answers. They did it for one of the things, so it was very interesting. So yeah, I managed to detect a few people's errors and just change them. But yeah, please try avoid doing that. It just makes it easier for everyone, and also you can potentially lose marks if neither of us pick it up. So yeah, also just check that out. You'll see all of in the spreadsheet, it has all of the things you entered in, so you can see and compare it to the announcements I've sent. Okay, good. So there we go. That's an update on that. Let's do this question. We're dealing with 3 phases now. You know your 3 phases. You have your y and your delta. Either you can connect them like this. That's a delta, like delta time. Or you have y, like a y, like this. These are three sources that are 120 degrees out of phase. Yeah. So let's do question 1 of this, and it says write down the phase voltages. Okay. So let's look if they were first. Let's just analyze our question. Three-phase Y-connected load by balance is supplied by a balanced three-phase Y-connected source. Okay, with a voltage of 120 volts RMS. Okay, cool, RMS. The line impedance and load impedance. So we'll have the line impedance and load impedance per phase is this, and then the load impedance is this, respectively, which will determine the value of line currents and the load voltages. So step 1, write down the phase voltages. Okay, so now this is a theory question. First, we would write 120 volts, well, we'll do the volts afterwards, at an angle of 0 degrees, VRMS. Okay, RMS. This is phase A. What will phase B be if this is phase A? This is like standard notation, so you do actually need to know this. What will its phase be? It's going to have the same magnitude because it's balanced. I don't think I'll be able to see the chat. I hope so. Someone type the phase. Let's see if I see it. And then if someone types it and I don't see it, I see it. Okay, there we go. Then someone else would have to say it. Okay, cool. Exactly. So it's minus 120 degrees, VRMS, and then 120 at an angle of minus. Wow. Good. RMS, thanks. Thanks for the interaction, guys. Okay, there. So that's phase A, phase B, phase C. So you see, this is we're going around the circle. If we had a phasor diagram, we'd say we can choose any one to be a reference because remember, phases are these things that rotate over time. Remember, we did this whole thing when I was back in the day when we were looking at that they're actually just causes. It's a whole beautiful thing of using Euler's identity in a way to represent cos waves, and then you can add them together and treat them like vectors, and all this sorts of crazy stuff. So yeah, the main important thing is the difference between things, because they're going to rotate, they can be anywhere. It's actually the spatial difference between them that's important, and we can set one as a reference. So we'll say that phase A is our reference, so we can call that as 0. And we're going to keep it at 0 because they all rotate together, so we can just analyze their relations amongst each other by just keeping it stationary. Definitely look more into phases. They're very cool things. You can just do intuitive vector maths with causes and sines. You'll see you get lots of trig identities actually from this. Basically here we have 120 degrees between all of these things, but we say that this is positive because that's just our standard notation. So to go backwards is negative. And if we label this as A, this is B, and this is C, then it's clear that B must be minus 120 degrees from there to there, from 0 to minus 120, and then C will be another minus 120, so it becomes minus 240 degrees. Okay, so those are our phases. That's question 1. Sweet, write down your phase voltages. Phases are also referring to these individual supplies. These are your phase voltages, and the current that flows in these phases, so you use 3 of them, 3 phase, that is your phase current. And then when you go to lines, we'll deal with line voltages, line to line, and then we'll also have line to line, which we'll deal with. Okay, so draw the per phase diagram. Okay, so just to draw out the situation, what's happening, they say a Y connected to a Y, which means we have this, a Y on one side, and then we're connecting it, probably with some line impedance, to a Y orientated load. So when you're dealing with 3-phase power, you're not just dealing with your supply being phase, you also have your load being 3-phase. So you specify if it's Y or delta. So just drawing this very quickly. And this is entering what each of the things are. They say that this is 1 plus by 1 J for the line, and they say our load is 20 plus by 10 J. So this is what's happening as a whole. We can call this phase A, phase B, phase C. Remember with this, we also have this common point, which is a neutral. You don't theoretically, you don't need this line. But it's like if there's imbalances there, actually current does flow down here. But they will flow primarily between the two lines when they're being transported. Okay, so now they say draw the per phase diagram. Okay, now the per phase diagram, why we can immediately draw a per phase diagram very easily is that if we look at this, can we see that there's kind of a symmetry? We can actually just isolate a phase like this. Guests are waiting to join. View lobby. In meeting, how do I let these? This admittal. Why isn't it going? Admit. 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 Maybe it's just glitched. It's okay. Sick. So yeah, you can just isolate them immediately because it's Y. Can you see this is kind of, if you look at this to here, that's kind of another phase. And if you look from here to here with that neutral line, it's kind of another phase. If it's Y to Y, you can kind of isolate your phases very easily, as opposed to, let's say one of them are delta. So we'll keep our load as, our source is Y. Then we'll connect this to delta like this. And what you'll notice is that to isolate a phase is not as easy to do. Because look, let's say we want to draw a circle around one phase. Can you see that over here we get to this point and this point, and you can't actually isolate this load by itself. You'd have to kind of draw around the whole thing, if you see what I mean. There's a cable going there and a cable going here. Whereas with this one, there's just a cable. So you can just isolate into 3 separate phases very easily. So if you want to draw your per phase diagram, can you guys admit guests so I don't have to go back? Or am I the only one that can do it?
We can admit them.
Okay, sick. So if I want to draw phase A by itself, I can do something like this. So now we're just drawing the circuit. Here's that neutral wire, that's this wire over here. And here's going up to the load. 20 plus by 10 J. Someone's mic is unmuted, but I can't quite see right now. Okay. So this is your phase, and this is your load. I'll just call it LP to not be confused with line to line. So LP is for the load per phase. From here, this is our per phase diagram. Okay, so we've done that. We've drawn our per phase diagram like this. So that was 2. It says find the line currents for phase A. Okay, so we've called it phase A, and we're going to find the current. Now to find the current, the current for the phase, there's a few things to consider. It could be the current for the line or for the phase, but in line to line, we can see that the currents are the same. The ones that are in the phase are the same as the ones in the line. It's one of the reasons why we can actually draw the per phase system like this. But let's find this actual current. Let's see if we have a voltage across these two, we know what the voltage is from here to over here. So we know the voltage across two resistors. Then if we do the division across those two resistors, we can find the current that flows. So we could say that IP is equal to VP divided by, we'll say ZP for the load. We'll say Z, yeah, why not ZP, like the phase value of the load, which is just this, because you can see the phase is just what we're dealing with in that kind of circle there. That's your phase. These are each phases. Okay, so if we were to do that, we'd see that our voltage, I didn't label the voltage, it's 120 RMS at an angle of 0. This would become 120 at an angle of 0 divided by 1 plus by 1J plus by 20 plus by 10J. Okay? And now the resulting complex number we will get is another phasor. And remember, phasors are representing sinusoids. They're representing causes and sines, depending on their phase. And now by dividing these two things, we're going to get another sort of, I'm just putting in my calculator, plus by 20, plus by 10. So this you can literally plug in straight into your complex mode of your calculator and then convert it to the sort of phasor form. It's always useful, rather than when it's the like the mod arg form. Does everyone know how to do that? Your calculator can do this for you. I'm going to do two decimal places here. Minus 27.65 degrees. And this will be amps, RMS. Okay, so we're going to get, by inputting a sinusoid, okay, with a magnitude of 120 RMS, RMS meaning that it's average sort of power, the power that it would dissipate through a resistor. So that's not its peak value. You times that by square root 2 to get its peak value, but you're inserting this sine wave. It's going through a load that's like some sort of a resistor and an inductor. So two inductive loads here. Remember, inductors are this formula. I'm just giving a perspective of what's actually happening. It's V is equal to L di dt. So we're differentiating a current, or you could say you're integrating a voltage. And remember, when you differentiate or integrate a sine wave, you get a kind of shifted sine wave with a magnitude change. Yeah, so phasors beautifully do this all for us by just doing this complex division on a bunch of constraints that everything's moving in kind of the same way. We can just do a simple division like this with complex numbers, and it will represent actually taking derivatives, because you still get causes and sines out. As we can see, our answer is still the sinusoid because it's a phasor, which is quite interesting. All of our answers are actually going to be sinusoids. We put a sinusoid in, we get a sinusoid out. Quite beautiful. I don't know if you guys are following that, but that is quite a cool thing. If maybe you have lost perspective for what's actually happening when you do these calculations, but yeah. So I get 5.06 minus 27.65. That is the answer in the book that they suggest for question 3. Is everyone clear on how I got there? It was just simple division of two complex numbers. If you wanted to do it by hand, you'd convert this, well, not in your calculator, you would convert this into mod arg form, like that. And the way that you do that, this is just the square root. So basically, if you have a real part and imaginary part, okay, this you can look at as a vector. like this. So this will be something, if this is imaginary and this is real, you'll get some point here, and this you could say it's a plus by b I, okay? A for the real part, and b for the imaginary part, the magnitude of that. We can convert into this. I'm just going to show it briefly. By, I shouldn't use a here, we'll call it r. Instead, what we want to deal with now is we want to deal with a theta and this distance. Okay, cool. So if you want to find this distance, can you see this is just a right angle triangle? Okay, so we could find that distance. We'll call it r. Remember Pythag, just like r squared is equal to imaginary squared plus by real squared. Okay, or you could just say it's the square root. I'm just recapping all of this sort of stuff just very quickly because I think some of us, I'm not surprised if some people maybe don't know what's happening. They're just learning formulas, so hopefully this will give that context. I'm sure for some also this is just like, what are we doing? This is it's too easy. But yeah, so then that becomes the imaginary squared plus by real squared. And then that will give you the distance of your triangle, because now we're dealing with distance and angle. If we wanted to find our angle, we could say tan to the -1 of the opposite, which will be imaginary, because the opposite is this side from the angle, and then the adjacent, which is real. So then you'll do tan to that, and then you could do it like that. And then from there, you would do the division. And then that would just mean over here, this would become some sort of number with an r and a theta. If you do a division, it will just become 120 divided by whatever that radius is, and it'll become 0 degrees minus whatever the phase was. And that's if you do it by hand, but our calculator does that for us. Are we all aware how to let the calculator do it for us? If you type in your number, it will give us it always gives it to you in the complex mode as a plus by bi. But if you go shift and then you say complex, so you go shift and you click 2, which says above it complex, CMPLX. Okay, so you do that, shift 2, and then you click the option that says r theta, which you click the number 3. And then that will take whatever the number you've just put it in, you click equals, and we'll put it into that form. And that's how I did that. Okay, very basic. Just make sure that, I'm just making sure that everyone knows that, because it's a huge save. Anyway, let's continue. It says find the load voltage for phase A. So what we're looking for in our diagram here, we're looking for this from over the load, the voltage over there where those orange dots. We know what the current is now. So how can we find the voltage? Well, we times our current times by our load, and then we'll get our voltage over that. So if we want to find the voltage over the load, we'll say LP for the load phase is equal to the current in that phase times by the impedance of the load per phase. So I'm just writing it like that. So that will become 5.06 at an angle of minus 27.65 degrees. Okay, I'm in degrees as well. That's the thing you need to consider when you're doing these complex things. Are you in degrees? Are you in radians? We times our load. What is our load? 20 plus by 10. Look, we're literally doing normal circuit analysis, except we're using complex numbers. How amazing. That's what phases does for you. If you actually didn't have phases and you're trying to do this by first hand, you'd be solving differential equations. Believe it or not. So yeah, don't lose sight of, but that's because when you derive a cos, you still get a cos. Derivative of cos is sine, it's just a shifted cos. Whatever, you know what I mean? That's the simplifications we're making. Anyway, let me put this into my calculator. We'll say minus 27.65 times by 20 by 10i. And here we go. Then I say shift 2 for complex, click 3, make it into the mod.arg form. And what do I get? I get 113.15 at an angle of minus 1.08 degrees. And this will be VRMS. So that's what VLP is over here. We just times the current with the impedance. Okay, let's see if that's the same I got earlier. If it's the same from the book. On 135. Just double checking. Angle of, yeah, what does the book get? The book gets that as well. Okay, tick. Nice. If you're doing work by yourself, and you trying to see if you know things, if you get the right answer, please give yourself a big green tick. You know, if there's green, it's even better. your brain will love it. But give yourself a good tick. So like if you get it right, be very proud of yourself, even if it's the most easy question. You need to keep your spirits high. So when you're testing yourself, it's like someone has given that tick to you, but you're giving it to yourself. But yeah, feel proud of yourself. Then it says find the corresponding line currents and load voltages for B and C. So all that would happen there is that for B, it would just be minus 120 degrees phase shifted, and then for C, you'd minus 240 degrees to this. And then that would give you the whole total picture. If they wanted to know what the power was, okay, for a three-phase system, this is quite good to mention. Power for a three-phase system is, we know normal power, you can just say voltage times by current. Here I've written as V phase, I phase. If you times these two together, you get power for one phase. And then amazing, when you're dealing with energy, you just times it by 3. There's no fishy, weird square root 3s happening, or all this sort of stuff. Well, there is for the one, if you did it for line to line. But this is just 3 times by that, by your voltage times by your current. That would give you your power for this circuit. So yeah, that's how you can remember that. So far, are there any questions? I don't know if this was clear.
I have a question about the power. Would that be real power or the apparent power that you work out?
Okay, good question. So if we look at V phase, what is our value of V phase? Whatever it was, let's say it was 120. It doesn't matter, whatever it was. Basically, you'd be timesing complex numbers here. So a complex times by a complex, okay, would give you a complex number. What is a complex number? A complex number is this. So it has an imaginary part and it has a real part. Okay, so when you get that complex power by timesing two complex numbers, if it's going to be real power, you're taking the real part of that. If it's going to be the reactive power, you're taking the imaginary part of that. If you take just the magnitude of this thing, then that is your apparent power. So by default, this thing is all three of those things. Depending on how you look at it, if you take the magnitude of it, then you get apparent. Because remember, you don't give apparent power is not a complex number. It's a real magnitude. So you give the magnitude of that complex number is your apparent power. If you take the real part of 3VPIP, then you get your real power in watts. If you take the imaginary part of it, 3 times by VP, don't ever get confused. We're just timesing complex numbers. We're just doing maths. Just normal old circuit theory. If you take the imaginary and then you just deal with the complex number into reactive and real parts. And then this would give you the imaginary power in VA little r. We have a unit that signifies that it's reactive. Yeah, if it's real power, we say it's watts. If it's apparent power, we just say that's this VA, because what we do to get there? We just times voltage times by current. That's why it's VA. Okay. So yeah, when you times these two things, what do you get? It's all of them. Do you see what I'm saying? The magnitude of it will be apparent. That will be from here to here, the distance, the magnitude.
Thank you.
Okay. Well, there we go. Let me just double check if there's anything useful I can give to you guys. Let me just look at my notes quick. Is there anything that I've forgotten? Are you guys finding this all right?
Sorry.
Hello?
Oh, can you explain on the last part, question 5? I didn't get something what you said there.
For question 5. Yes. Okay, so for question 5, basically, I just said you shift your answer by this magnitude. So minus 120 for B and minus 240 for C. How you can think about that is that, did you see that for all of these things, we were timesing or dividing? Okay, we were timesing or dividing. There's no additions of things. We're timesing it there, we were dividing over here, we were timesing. Remember, if you times two phases, let's say R1 theta 1 times by R2 theta 2, that's the times. That'll just be, the resulting thing will be R1 R2 theta 1 plus by theta 2. Okay, so now because we are timesing the whole way, you can just add it in at the end. So like, let me just double check. You see, they want the line currents and load voltages for phases B and C. So before we were working them out for A. Okay, this is for phase A, this is for phase A, for 3 and 4. All that would happen is that over here, where we just wrote as an angle of 0 degrees, here we would actually write minus 120, okay, for B. Okay, so then basically that would happen over here, we would get an additional minus 120, minus 27.65. Okay, so then that would be one thing. We just got an additional, that's just for the angle. The magnitude would be exactly the same because it has the same magnitude. Still 120 over there. For this part over here, when we're timesing the two of them, okay, now our current, this one, would become minus 127.65. Okay, and then because we're doing multiplication, then our final answer here would just get an additional minus 120. You see, I'm just showing the whole process of how, if you were to just start your calculation with B instead, phase B, which is 120 at an angle of minus 120 degrees, you just eventually end up just with a phase shift of minus 120. That's what I was saying over here, that you just minus the phase. The magnitudes will all be the same. The phase will just be different.
Okay, thanks.
Okay. Yeah. Any other questions, guys? I think this is pretty much as far as I think you guys have gone. Just to give context of why you guys are doing 3-phase now, I don't think generally you normally do 3-phase in second year. It comes late in your life. But what was happening is that students were getting too overwhelmed with 3-phase, because you'll see what you end up doing with 3-phase, and it is intimidating, but it's actually not. It just feels intimidating, is that now we actually use transformers. Don't be scared. You're not doing this year. But basically, for each one of the phases, there will actually be a transformer associated to each one of them. So there'll be like this whole little, how you have with the other transformers equivalent circuits and all that sort of stuff. That's going to be happening for 3 of them. This is how we distribute our energy. When you see those big boxes and stuff, this is what's going on in the 3 phase. So now we just do breaking it into 2 steps where you're basically just doing it with given a voltage. Now this voltage later in your lives, that voltage is actually going to come from a transformer ratio and transformer relationships. But for now, you're just dealing with it as a voltage source, and the load is just as a load. So this is all you're doing. So these basic sort of circuit things is pretty much the extent of what is required. It's literally just an introduction to get you guys ready. So yeah, so don't be too scared. It's really not going to get much harder. The last thing that has been like briefly introduced is this concept of power factor reduction. I think let me just speak a little bit about that. We know if we have a power, okay, and we call our power factor the angle to which our current lags our voltage, okay. So if this is current and this is voltage, there's a lag between the 2 of them. Okay, that's our angle. Basically, what ends up happening is that as your voltage is going, there's a delay. Okay, and what's actually happening is that because of your derivatives like di, dt, and dv, dt, where you're doing your little derivatives, you actually storing energy. You're storing energy in electric fields and in capacitors. You're storing them in magnetic fields and inductors. Okay, it's actually the wrong way around. This is with but don't worry. And what ends up happening is that what you actually send to your motor, let's say, is only the real part. There's going to be a whole bunch. If you draw your little pi triangle like this, there will be the apparent, the real, and the imaginary. The actual thing that's doing the work, that's actually going to cause things to move in the motor, is only your real. The imaginary power, okay, remember the impedances is like JW, JWL, F, or whatever. This is the impedance for an inductor. And then a capacitor is like 1 over JW, CF. It's something like this. These impedances are purely real and purely imaginary. So they cause your reactive power. They're actually called reactive components, inductors and capacitors. And the reason why is because they react. They don't actually dissipate energy, but they store energy. Okay. So they store it in time. So that's what this delay is. This is energy that's been stored and then released later. Now that's not desirable because it's your per second power that's going to be doing things. This is your real power. So if you look at times these 2 values together, that's the actual power that's going to be delivered. Can you see that if they're more aligned with each other, it's like more in sync. You get more of the power that's not being stored in capacitors, but actually doing things. So that storage of things in capacitors and all sorts of stuff, you can actually be charged for that because a power station still has to supply that. It has to supply your what you demanding. It actually has to supply this amount, the apparent. And so it fills up all of your capacitors and inductors so that it can operate and produce your real. So you want to actually minimize this. So if, let's say, it's an inductive load, which means that it's going to need some sort of current, okay, current storage, you can actually use a capacitor to store that energy. And instead of it having to survive by the power station, it will be supplied by the capacitor. So it will actually cause maybe the voltage to become more aligned or whatever. It doesn't really matter. But yeah, so this becomes the supply, not just the station. You actually add additional capacitors, you'll see, to counteract the delay, which is quite amazing. So that's why, because you actually just, yeah, the capacitors start to supply your things. That's essentially what's going to happen, and you pay less electricity for not making the power station account for filling up these things, these demands. That's kind of another way of how things are going to be explained to you next week. But yeah, there we go. Very all over the place. Hopefully there's a bit useful here in this mess of writing and color and a question. But yeah, at least now you can see you have a memo for example 9.1, which will definitely help you guys out. So yeah, that's that. That was a nice quick and dirty tutorial. Is there anything you guys would like to ask while I'm here? Anything that's kind of been bothering you? Maybe something about the quiz that you'd like to discuss? Yes. Ruth Ann.
So when I was studying for the test, I saw that underneath transmission lines, you also and waves. There was also in the green book about standing waves. I assume we're not expected to know that because we weren't taught it directly. It's just in the green book.
Yeah, don't worry about standing waves. They're very cool though. This is another one of those topics that's going to come up later in your lives. But no, right now you don't need to know standing waves. I can explain them to you briefly just for fun. What's happening? It's very cool. So you get this thing called resonance. Okay. So what ends up happening? So we've been only dealing with pulses that travel down lines. Like we close a switch like this. Okay, we close the switch, which means that the voltage over time will have like a voltage wave or whatever that will travel. It will go from being 0 volts to 5 volts. If this is like 5 volts on this side, it'll go from 0 volts to 5 volts. Okay, as we close it, you see it's a step. What you can actually do with transmission lines, and this is a big thing to consider, specifically if you see now that we're dealing with AC power when you're transmitting it. So from our power station, we put them on transmission lines, these AC waves, even though we're not dealing with AC waves, we haven't taught it. But this is the real thing that's going to, what's actually happening. You definitely do it for DC pulses. That's what's my kind of specialty, is more this sort of stuff. But this is where it's also huge when you're sending power around the country over these long distances. They're here. We have to account for the delay caused by the travel of these thousands of kilometers. What ends up happening is that you get a sine wave that will go forward. Okay, let's say that this load is not matched. Okay, a sine wave will arrive at the load. Okay, one that comes this way, and one will get reflected backwards. Okay, and it will also travel. Now, what's going to actually end up happening is that on this line, these two waves add together, okay? And it turns out when you add two sines and causes together, well, these two waves, sometimes you can get another sine wave, but you get this sort of wave that oscillates with standing points, standing little nodes. So these two waves add together, and you kind of get this stationary wave in certain scenarios. And then this has twice the amplitude. Wait, should I see if I can get an example of this? Standing wave. And you can get things in between. It was actually explained at that video in the beginning when I started teaching you guys. I had that video. They explained the standing waves. That's exactly what it is. That's probably way better than I can explain it. That guy explains it so well. Let me see if I can show the two waves adding together. See standing wave. Yeah, I think this is going to be the one. This is going to be the one. Let's just see. Oh, yeah. This is the one. Okay. Copy image. Sorry, last thing, and then we'll call it a day. We'll have a nice short tutorial today. Tutorial. Here we go. Let's paste this. Okay. It's going to arrive. Just let my things sync up. If I go, so here's the guide. That's not animating anyway. Let me just show you. It's interesting. Wait. Standing wave. Okay. Which one's going away? Was it? Just one with the different colors. Here we go. Yes. Okay. So all this time to show you the thing that you don't even need to know right now, but it's definitely cool to see. Here we go. Standing wave. Can you see? In red, we have a wave that's being transmitted down the line. In green, we have a wave that's being reflected. Okay, hopefully it's clear. Oops. And then the blue one is when you add those things together, which is beautiful. Can you see that they cancel out completely in one point, and then other points they add up and they actually become double the amplitude. This is resonance. This is in time we constructively interfere. So by having the forward wave constructively interfering with the negative wave, we get a wave that's twice the height. It will be a bit less than twice because there'll be a reflection coefficient added onto one of the waves, so it'll be less than, it can be maximum twice, but it'll be a little bit less. But yeah, this is what happens. This can be problematic if you're rating things to carry a certain voltage and suddenly they're carrying way more than what you thought. Definitely a hectic thing to consider. So you actually have to do all strategies around this, and that's why you guys teach it. But you should go for fun. Add a cos wave traveling with time and a sine wave traveling in the reverse direction in time, and you'll see that you get another cos wave. It's weird. You'll actually find out that that's one of the identities that you just learn. One of the cos identities. Like one of it will be either one of the double angles or something crazy like that. But it's quite amazing. So yeah, there we go. I think this is also how strings I think can actually oscillate a bit like this. There's some sort of resonance it will vibrate at its sort of resonance at the speed of things traveling down it. But yeah, there we go. That's a little bit of insight, a little bit interesting that. Yes, I have a question.
Can you hear me?
I can hear you.
Okay. I have a question in terms of like the quiz we just wrote, the one quiz 5.
Yes.
So like I'm looking it over and I'm looking at my mistakes, and for question 4, I just want to verify a few things. Would you mind just doing it?
Question 4.
Yeah.
Let me see if I can get it. So question 4 says, what is the inductance per length for the transmission line?
Yeah. So I got 2.5 times 10 to the power negative 4. So I was wondering, the units, they say they want them in
Millihenry per meter, yes.
yes. So would that still be, isn't it 10 to the power, should I convert it to 10 to the power 3, negative 3,
Yes, you
which
must.
is 0.25?
Which is, sorry, 0.
Is it 0.25 or does it stay 2.5?
So your answer that you got was 2.5 times by 10 to the negative 4.
Yes.
Then you've made a mistake, because yeah, it should be 2.5 times by 10 to the negative 3.
Okay. That means I
Yeah.
made a mistake somewhere.
Yeah, there's some small, you've made a little error, maybe with your capacitance. Did you see it's 1,000 nanofarads?
Nanos to the negative 9.
Yes,
Okay.
that's right. And then you'll see both of them. Yeah, then to get the inductance per length, you have your capacitance per length, and you'll have your characteristic impedance, and then you can solve for that using the characteristic impedance. You'll square the characteristic impedance, and then you know what I mean? Because the characteristic impedance is equal to the square root of the inductance per length divided by the capacitance per length, and then you'll solve for it in there, and then you should get the right units.
Oh, okay. So I need to say 50 squared multiplied by 100 times 10 to the power negative 9. Is that correct?
Yeah, I think so.
Can you quickly like put that in the calculator, unless my calculator is going haywire right now, because now I'm starting to think I should buy another calculator.
Let's say 50 squared times by 100 times by 10 to
it's 1,000 times
1,000, yeah.
Times by 20 as well.
Oh, okay. Okay, I see it now. Thank you very much. Times
Yeah.
by 20. I didn't use the 20.
No, you don't need to times it by 20. Because
Yeah,
this.
you do. Otherwise, you don't get 2.5.
What if
Yeah,
you go,
if we don't times it by 20, you don't get 2.5.
what if
That's
you
the
get
one.
50 squared times by 1,000 times by 10 to the 9?
By 1,000. Okay, let me. 1,000. Okay, by 1,000 I get it as well.
Yes, you don't need to times it by the length here.
Okay, thank you very much. Also,
Yeah, so
yeah, you can continue.
no, I was just saying for the capacitance, for the characteristic impedance, because it's a ratio, you can use the per length or the total capacitance, because the ratio will be the same. So yeah, because if you do the ratio of the total capacitance, the total inductance and the total capacitance, that's the same as the ratio as the per length inductance and the per length capacitance, because you're dividing the two. But when it comes to phase velocity, you're timesing the two of them, and that has to be per length, because the product of the two things is different. The product of the per length capacitance times by per length inductance is different than total inductance times by total capacitance, if you understand what I'm saying.
Yes, I think I get what you're trying to say. The last question I have is about question 7. Would you mind doing that question so that I'm able to do 8 and 9, because I didn't get them correct?
What is the voltage at the load when T is equal to T? So that's the voltage when. So T was defined as the time it takes for the signal to travel to the load. Okay. So at time equals 0, we close the switch, and then it's going to take capital T seconds to get to the load. So then what is the voltage at the load when T is equal to T? Okay. So let me just do it because you need all your reflections. So that's going to be the forward going wave plus by the reflected wave. Let me just see. Let me just see if I have it here. So this is question 7. What is the load? What is the voltage load when T is equal to T? Yeah. Oh, okay. No, I was looking at a student's answer, and I thought it was the answer. Yeah, so that would be the initiated voltage plus by the reflection coefficient times by. So let me show you the diagram, and then I'll answer Liam's question if he's still here. Let me just share my screen. So if we go like this, remember, so we have our transmission line like this, okay, and we're saying this is the transmission line, here's the load, here's the transmission line, here's the switch that's just being closed, here's the supply, there's also a resistor here, whatever. When it's saying that T is equal to T, now T is the time it takes to get to the load. At T is equal to T, that means the voltage that was initiated here arrived at the load. Now, to understand what's going to happen, you must draw your reflection diagram. Okay, so this is, remember, this is time on the vertical axis, this is position. So position is where you are on the line. Now we know that a wave will travel in time and it's going to travel in direction, the initiated wave. Okay, so together that's going to do something that's doing this in time and position. Okay, so it will go like this. Okay, how long will it take? What is this? If we measure from here to here, which is the same as this, it's just showing it on the axis. What is this thing that I've labeled A? What distance, this is a certain time. What value of time will that be? From the question, it will tell you. What value of time will that be? Do you know?
So it's from the time that we get divided. Is it the whole time there, or is it the half of the time? Like
so this is T. So it's the time it takes for a signal to travel from here, the source end, to the load end. You see, so it's traveled that distance, and it's taken this amount of time that we labeled as T. Okay, so that's what the question says. It takes this amount of time to travel this distance. Okay.
Oh, okay.
So what happens?
I see that my first problem is that I counted that 2 times. I also counted for it returning back to the source. Okay.
Yeah, okay, so then that would be a very good question for me to give you. I could say that the time it takes to go there and back is T. I could say that, and in that case, then it would be half. And then you would be able to have to do the calculation like that. And I could very easily do that. But yeah, so you need to understand exactly what's happening. So there we go. That you must try it with that. Let me just give you the next step, and then from the rest you should be able to work it out. This will make a huge difference. If you didn't have this, you're in big trouble to try get it right. But what happens is that as this happens, at t is equal to that time, at that exact moment, a reflected wave is initiated. So the value, okay, wait, so if this has a value of V naught, which is the initiated voltage, what will be the value of this reflected wave? And we'll say that there's a reflection coefficient over here. We'll just call it reflection X, whatever. What will what will that be? What will the value of the reflected wave be?
Initial multiplied by the coefficient.
Yes, it'll be the coefficient. This is the reflection coefficient that tells us of the incident wave, which is this initiated voltage. That's this one here. This is the incident wave. We times that incident wave by the reflection coefficient. Exactly. So now if I were to say what is the voltage over there, it would be the voltage of that. It will be the sum of the waves that are present there. So it'll be that plus by the reflection coefficient plus by those times by V naught, like that. So it'll be the sum of those two things. What's very important to note, okay, so that's pretty much what you do for that question, and you'll see you'll get the right answer. Let's just label our time here. Let's just label time, so this will be 0. This will be t over here. Here it'll come back at 2t. Now it'll be back at the source. Let's just say if I ask what was the time, what is the voltage at time equals to 3t. So 3t, it's arrived back again. What it would be at 3t, it would be the sum, okay, of all these waves. Then I'm going to label 1, 2, 3, 4. So it would be 1 plus by 2 plus by 3 plus by 4. All of those values, because they've existed. You see it existed there, it existed there, it existed here, it existed here. So you have to add them all up to find the total. And then you can do that for any amount. If it was whatever time later on, you just have to make sure that you add all of the waves before to that point.
Okay, thank you very much. I see my mistake now. I didn't label the T's as I should have. That's not the problem.
Okay, so you understand all of this, the rest of this stuff.
Yes.
Where you add it like this. Perfect. Yeah. Okay, cool.
Thank you.
Okay, let's just go back. Is there any other questions? Are we all good? I'll give you guys a little bit of time to think if there's a last question you would like to ask before I continue. I'll even put my own hand up. And no, I won't. I can. You know, when they do that, they put their own hand up. No one's putting their hands up. Okay. Well, then I think that's that. Thank you guys for joining the tutorial. Let me know if there's any queries. Write them in that form, and don't put an X in that form. Some people are putting X's. That's for me to say I've dealt with it. So leave that blank, else your thing might not be dealt with because I think it's dealt with. So there we go. Good job, everyone. Good luck with the work. It's not so hard from here on out. All of the stuff that we're going to do is pretty basic now. This three-phase thing is a bit hard to kind of think about, but don't think too hard about it because it's just the beginnings. It's quite basic. Don't overthink it. And then, yeah, good luck with everything. So bye.